Alright, let's get started. Logical and relational operators. The relational operators take operands of arithmetic or pointer types. The logical operator takes operand of any type that can be converted to bool. Then if these operators all return values of type bool, arithmetic and pointer operands with the value of 0 are false, all the other values are true. Okay, important. Uh, the operands of to these operators are R values and the result is R value. Okay. This is logical and relational operators. This is right associative, not okay. From right. This is left associative. Associativity is left, and operator is this equal to equal to. Okay. Logical and or. The overall result The overall result of the logical AND operator is true if and only if both its operators evaluate to true. The logical OR operator evaluates as true if either of its operand evaluate as true. Okay. The logical and OR operators always evaluate their left operand before the right. Moreover, the right operand is evaluated if and only if the left operand does not determine the result. Okay. This strategy is known as short circuit evaluation. The right side of an dead is evaluated if and only if the left side is true. The right side is evaluated if and only if the left side is false. Okay, that is the main difference in both. Okay. So several of the programs in chapter 3 use the logical AND operators. Those programs used the left hand operand to test whether it was safe to evaluate the right hand operand. Right. Right. First checks the index has not reached the end of the associated string. We're guaranteed that the right operand won't be evaluated unless index is in range. As an example that uses the logical OR, imagine we have some text in a vector or strings. We want to print the strings adding a new line after each empty string or after a string that ends with a period. Okay, so we will use OR if this is a period. If it is empty or if the last thing is a period. Empty, we will use the range space for the loop, and then we can process uh, each element. Okay. After we print the current element, we check to see if we need to print a new line. The condition in the if first checks whether s is empty. If so, we need to print a new line regardless of the value of the right hand operand. Only if the string is not empty do we evaluate the second expression, which checks whether the string ends with a period. In this expression, we rely on short circuit evaluation of logical and or to ensure that we subscript s only if s is not empty. It is worth noting that we declared s as a reference to const. The elements in a text are strings and might be large. By making a reference, we avoid copying the elements. Okay. Okay. It is worth noting that we declared s as a reference to const. The elements in the text are strings that might be large. For making as a reference, we avoid copying the element, but we don't need to write to the element. We made a reference const. Okay. Logical NOT operators. The logical NOT operator returns the inverse of the truth values of its operands. We first use this operators here as another example, assuming vec is a vec is a vector of ints we might use a logical NOT operator to see whether vector has elements by negating the values returned by empty. The sub-expression evaluates as true if the call to empty returns false. Okay. The relational operators, okay, they are left associative. So, okay, the relational operators have their ordinary meanings and return bool values. These operators are left associative. Because the relational operators returns bool, the result of chaining these operators together is likely to be surprising. Oops condition compares k to the bool result of okay, so we associate from left and we evaluate them. So I less than j, this will be 1 or 2. Okay. Okay, this condition gives I and j to the first less than operator. The bool result of that expression is the left hand operand. The bool result of that expression is the left hand operand of the second less than operator. That is, k is compared to true or false result of the comparison. To accomplish the test we need, we can rewrite the expression as follows. Okay. Okay, condition is true if I is smaller than j and j is smaller than k. Right. Then we have equality test and bool literals. If we want to test the truth value of an arithmetic or pointer object, the most direct way to is to use value as a condition. Okay, value is true if it is not true. True if value is 0 is in any non-zero. In both conditions, the compiler converts val to bool. The first condition succeeds so long as val is non-zero. The second succeeds if val is 0. We might think we could rewrite the test of this kind. If val equals true, true if only val is equal to true only if val is equals to 1. Okay. There are two problems with this approach. First, it is no longer and less direct. First, it is longer and less direct than the previous code, although admittedly when first direct C++, this kind of abbreviation can be complexity. Much more importantly, when val is not a bool, this comparison does not work as expected. Okay, if val is not a bool, then true is converted to the type of val before the equal to operator is applied. That is, when val is not a bool, it is as if we had written equals 1. Okay. As we've seen, when a bool is converted to another arithmetic type, false converts to 0, true converts to 1. If we really cared whether val was a specific value 1, we should write the condition to test that case directly. Okay, it is usually a bad idea to use the Boolean literals true and false as operands in comparison. These literals should be used only to compare to an object of type bool. Okay. Explain when the operands are evaluated in the logical OR and equality. Okay. If the left operand is true, and if the and if the left operand is Explain when operands are evaluated. Equality operator. The evaluated. Okay, if the left hand operand is true and is left hand operand, the evaluated inequality. See, this is talking about equality operators, equal to, right? I guess in case of equality operators, both need to be evaluated. Okay. Okay, explain the behavior. Explain the behavior of the condition in the following. Okay, so we have a pointer. We are dereferencing CP, it will get H and CP. CP is a pointer which contains an address which contains an address. Okay, here CP is a pointer. CP is a pointer which contains the address. Let's say okay, so here CP is a pointer which contains an address, numeric type, and when we dereference CP, we get the character H. Is also numeric type, hence the whole expression evaluates to true. Okay. Do I need to do that? We'll check it out. Write the condition for a while loop that would read ints from the standard input and stop when the value reads. Okay, when the value reads to okay, when the value reads to, that is easy because section. Okay, this is exercise, this is algo section, right? Section 4.2. Okay. Section 4.3. Okay. This is 4.9. 4.9.cpp. Const cast hello, then FCP and CP. Expression evaluates to true. Yeah, okay. And we have write the condition for a while loop. Okay. Oh, sorry. Okay. I think this is 4.10. Okay. So while and temp is 0. Temp. Okay. This is left while C in temp. Okay, so it gets the value of and temp not equals to 42. I can do that. So it will evaluate the left expression first and then check the operand first and then check the right operand. So I can just say out of loop so I'll go 56, 45, 40, 42, 45. Okay. Write an expression that tests four values ABC and it shows that A is greater than B, which is greater than C, which is greater than D. Huh. Okay. Write an expression that tests four values A is greater than B. It is 11, right? Yes, okay, it is indeed 11. So we have write an expression that tests four values A, B, C, D, ensure that A is greater than B, which is greater than C, which is greater than D. Okay, so we'll go int A equals 4, B equals B, C, or D. Okay, I'll go bool result if A is greater than B. If A is greater than B, then check B is greater than C. B is greater than A is greater than B. Then check B is greater than C. Then check C is greater than D. Okay. So first we check A is greater than B. Then we check B is greater. B is greater than C. Then we check C is greater than be true, else false. Okay, so let's use this. I think उसके साथ experiment support है ना अभी रहने दो experimental support ठीक है तो okay so this is true then we have अगर मैं बोलता हूँ कि C को 1 कर दिया इसको 0 कर दिया 1 हाँ अभी भी ठीक है इसको 0 अरे इसको 0 कर दिया इसको 2 कर दो हाँ 0 ठीक है then we have this is also done assuming I, J, K are all ints explain what is so this expression means left associative less than K so in the end we are comparing the bool result of I being not equal to J with DJ K. If condition is true, we'll check 1 less than K. Condition is false, we check. Condition is false, we check 0. Okay. What is this? Yeah, I don't know. Alright. We have assignment operators. The left hand operand of an assignment operator must be modifiable L value. Okay. For example, this initialization, not assignment, modifiable. Okay, so we can initialize, not assignment. Initializations, not assignments. This is initialization. So each of these assignment is illegal. Because this is there is an R value, right? CI is say the const not modifiable. Okay, so this is initialization, not assignment. The result of an assignment is its left hand operand. Okay, the result of an assignment is its left hand operand, which is an L value. The type of the result is a type of the left hand operand. If the type of the left and right operands differ, the right hand operand is converted to the type of the left. Okay, so K equals 0. Under the new standard, we can use braced initializers on the right hand side. Okay, If the left-hand operand is of a built-in type, the initializer list may contain at most one value, and that value must not require a narrowing conversion. Error narrowing conversion. For class type, what happens depends on the details of the class. In the case of vector, the vector template defines its own version of an assignment operator that can take and initialize a list. This operator replaces the elements of the left hand side replaces the elements of the left hand side with the elements in the list on the right hand side. Okay, this went over my head. This operator replaces the elements of the left hand side with the elements in the list on the right hand side. Regardless of the type of the left hand operand, the initializer list may be empty. In this case, the compiler generates a value initialized temporary and assigns the value to the left hand operand. Okay. Assignment is right associative. Okay, assignment is not left associative. The result of an assignment is the left hand operand. Okay, left hand operand is the result. Okay, that is the result. But unlike other binary operators, assignment is right associative. Okay, each assigned. So we associate from right because assignment is right associative. The rightmost assignment j val equals 0 is the right hand operand of the leftmost assigning operator. Because assignment is right associative. Alright, so because assignment is right associative, the rightmost assignment j val 0 is right hand operand of the leftmost assignment operator. Because as its left hand operand, the result of the rightmost assignment j val is assigned to value I val. Is assigned to I val. Okay. Each object in a multiple assignment must have the same type as its right hand neighbor or the type to which the neighbor can be converted. Okay. Present pointer error cannot assign the value of a pointer to an int. String result. The first assignment is illegal because I val and p val have different types and there is no conversion from type of this to this. It is illegal even though 0 is a value that can be assigned to either of the object. Yeah. On the other hand, the second assignment is fine. The string letter is converted to string and the string assigned to s2. The result of that assignment is s2, which has the same type as s1. Assignment has low precedence. Okay. Assignment often occurs in conditions. Because assignment has a relatively low precedence, we usually must parenthesize the assignment. For the condition to work properly. To see why assignment in a condition is useful, consider the following loop. Okay, so we want to call a function until it returns the desired value, say 42. Okay, get the remaining value, do something. Here we start by calling get value followed by, okay, here we start by calling get value followed here we start by calling get value followed by a loop whose condition uses the returned value from the code. The last statement in the loop makes another call to get value and the loop repeats. We can rewrite this code more directly as better way to write a loop for the condition. Okay, so we assign first. Okay. The condition now more clearly expresses our intent that get the value first, then check. The condition now more clearly expresses our intent. We want to continue. We want to continue until get value returns 42. The condition executes by assigning the result of 42 to get value to I and then comparing the result that assignment with 42. Okay. Okay. Without the parentheses, the operand not equal to would be the value returned from the get value checked. Okay. The true or false result would be assigned. Clearly not what we intended. Okay. So, the relational operators, parentheses are usually needed around assignments and conditions. Beware of confusing equality and assignment operator. Right. The fact that we can use assignment in a condition can have surprising effects. This condition in this if assigns the value of j to I and then tests the result of the assignment. If j is non-zero, the condition will be true. The author of this code also almost surely intended to test whether I and j have the same value. Bugs of this sort are notoriously difficult. Bugs of this sort are notoriously difficult to find. Some, but not all, compilers are kind enough to warn about the code. Yes, this. Compound assignment operators. We often apply an operator to an object and then assign the result to that. Okay, compound assignment. Right. We often apply an operator to an object and then assign the result to that same object. As an example, consider the sum. Okay, sum plus 1. This kind of operation is common not just for addition but for other arithmetic operators and bitwise operators, which we'll cover. There are compound assignments for each of these operators. Each compound operator is essentially equivalent to, with the exception that when we use a compound assignment, the left hand operand is evaluated only once. Left hand operand is evaluated only once. If we use an ordinary assignment, that operand is evaluated twice. Okay. Once in this expression on the right hand side and again as the operand on the left hand. In many, perhaps most contexts, this difference is immaterial aside from possible performance consequences. Okay. So we have write the values of I after the assignment. So for I and D, I'll go 3 each, and here also 3 and 3.5 because they can be converted. Okay, explain what happens. Error can't assign to a R value and always true since I equals 42. Always true since I equals 42 returns I and that value is evaluated. Okay, so we have the following assignment is illegal. Why? Or how would you? It's illegal because there is no conversion between int star and int type. However, you can easily correct it by uh, assigning, where you can easily correct it by assigning pi separately. Okay. If they get ptr not equals 0, if I equals 1024. Okay, let me try the section 4.4, right? Let's move back. Hmm. Goes to section dash 4.4. This is 4.13. Okay, so we'll go with int I. This is initial I. Double D. D equals I equals 3.5. Print line. D and I. Okay, so I have dash L with C++ experimental. I think it's not declared. Oh, okay. So I would also have to tell the standard C++ 23 std printer. Yes, my bad. No, C++ experimental. Standard support. I think I might have written about it anywhere. Beginning. Curiosity. Print. There we go. Okay. So std C++ experiment. Okay. So that was my bad. std C++ experiment. So 3 3, yeah, I was correct. And when we do with I, D 3.5 and 3, right? Okay. Increment and decrement operators. The increment plus and decrement minus operators provide a convenient notational shorthand for adding or subtracting one from an object. Again, this notation rises above mere convenience when we use these operators with iterators because many iterators do not support arithmetic. Oh. Okay, so there are two forms of these operators, prefix and postfix. So far we've used only the prefix form. This form increments or decrements its operand and yields a change object as its results. The postfix operators increments or decrements the operand but yields a copy of the original unchanged value as its result. So this is equivalent to j equals 1, I equals 1, and this is j equals 1, I equals 2. These operators require L value operands. The prefix operators return the object itself as a L value. Okay. The postfix operator returns a copy of the object's original value as an R value. Okay, advice: use postfix operators only when necessary. Okay, readers from a C background might be surprised that we use the prefix increment in the programs we've written. The reason is simple. The prefix version avoids unnecessary work. It increments the value and returns the incremented version. The postfix operators must store the original value so that it can return the unincremented value as its result. If we don't need the unincremented value, there's no need for extra work done by postfix operator. Okay. For ints and pointers, the compiler can optimize away this extra work. For more complicated iterator types, this extra work potentially might be more costly. By habitually using the prefix versions, we do not have to worry about whether the performance differ matters. Moreover, and perhaps more importantly, we can express the intent of the programs more directly. Okay. Combining difference and increment in a single, dereference and increment in a single expression. Okay. The postfix version of plus and minus are used when we want to use the current value of a variable and increment it in a single compound expression. As one example, we can use the postfix increment to write a loop that prints the values in a vector up to but not including the first negative value. Okay, so we'll go. We can p begin and if begin is greater than equal to 0. Okay, so we have here the expression plus begin is usually confusing to programmers new to both C++ and C. However, this uses pattern is so common. C++ programmers must understand such expressions. Dereference first, increment later. Okay, the precedence of postfix increment is higher than that of a dereference operator. So this is equivalent to this. Okay, the sub expression p begin plus increments p begin and yields a copy of the previous value of p begin as its result. We have the sub expression p begin plus increments p begin and yields a copy of the previous value of copy. Okay, the sub expression increments p begin and yields a copy of the previous value of the p begin as its result. Accordingly, the dereference operand of the dereference is the unincremented value of p begin. Thus the statement prints the element to which p begin originally pointed and increments p begin. Okay. This usage relies this usage relies on the fact that postfix increment returns a copy of its original unincremented operand. If it returns the incremented value, we dereference the incremented value with disastrous results. Okay. We'd skip the first element, whereas if the sequence had no negative values, we would attempt to dereference one too many elements. Okay. Brevity can be virtue. Okay. Expressions such as can be bewildering at first, however, it is a useful and widely used idiom. Once the notation is familiar, writing this is easier and less error prone than the most verbose equivalent. Dereference. Okay. Plus plus. Okay. It is worthwhile to study examples of such code until their meanings are immediately clear. Most C++ programs use succinct expression rather than more verbose equivalents. Therefore, C++ programmers must be comfortable with such usages. Moreover, once these expressions are familiar, you will find them less error prone. Okay, then remember that operands can be evaluated in any order. Most operators give no guarantee as to the order in which operands will be evaluated. This lack of guaranteed order often doesn't matter. Okay, the cases where it does matter are when one sub-expression changes the value of an operand that is used in another sub-expression. Because the increment and decrement operators change their operands, it is easy to misuse these operators in compound expressions. Okay. To illustrate the problem, we'll rewrite. Okay, let me bring in my math notebook. We are about to go study math. Okay. To illustrate the problem, we'll rewrite the loop from this that capitalizes the first word in the input. Example used a for loop. Okay. Which is allowed, which allowed us to separate the statement that dereferenced begin from the one that incremented it. Okay. Replacing the for with a seemingly equivalent while. Okay. It's undefined. Okay, this results in undefined. The problem is that in the revised version, both the left and right operands equal to use begin, and the right hand operand changes begin. Okay. The assignment is therefore undefined. The compiler might evaluate this expression as either. Okay. Right. Okay. So I'll continue this next day.